In this lesson, we are going to continue our study of relationships between quantitative variables. So first, let's look at a regression line. This one is a little bit more complicated than the previous regression lines that we saw. So a random sample of 93 car models was obtained, and the highway mileage, Y, in miles per gallon, and the weight, X, in hundreds of pounds were recorded. And just note that the fact that X is in hundreds of pounds means something a little bit funny. So that means that a car that weighs 4,000 pounds, notice it weighs 4,100 pounds, as in 4100s, so you'll have X equal to 40. If you have a 3,200 pound car, that means X will be 32. And what comes out is this regression line. Y hat is 51.6 minus 0.734x. And we see the association is negative. As we expected, we thought that as weight goes up, MPG will go down, so that's certainly happening in this equation. So first, find the estimated highway MPG of a vehicle that weighs 2,800 pounds. Now note, you don't plug in 2,800 for X. Here you plug in X equals 28. So Y hat of 28 is equal to 51.6 minus 0.734 times 28. And these kinds of tedious calculations are why you have calculators. This is 31.048 MPG. So on average, the two magic words, cars that weigh 2,800 pounds get about 31 miles per gallon, and I think this is specifically on the highway. It doesn't mean every single car of that weight gets that MPG, just that the average of all cars that are that weight get that MPG. Okay, next let's interpret B1. Now you have to recall that B1 is actually the slope. So remember, slope is with the X, so the slope is this 0.734 negative. So M equals negative 0.734. And recall that slope is change in Y over change in X. Now change in Y is MPG. Change in X is hundreds of pounds. So what this means is as X increases by, now is it just 1 or, so X increasing by 1, it's actually increasing by 100 pounds. The MPG goes down 0.734 miles per gallon on average. And I guess we shouldn't say as X increases, let's actually be even more explicit. Let's say as weight increases, because technically X does increase by 1, but that's the same thing as saying the weight increases by 100 pounds. Now part C, does it make sense to interpret beta naught? Now remember that beta naught, or beta sub 0, this is the y-intercept, which in this case is 51.6. And think back to when you graphed lines in like Algebra 1, you begin by applying the y-intercept, and it goes on the y-axis, like this one would be up there at wherever 51.6 is. And then we'd have a line that was some negative slope decreasing. Now, when you're looking at the y-intercept, x is always equal to 0. That is always true, and that is something that I will be checking if you understand. So to check and see if this makes sense, you have to plug in x equals 0 and see if this means a reasonable thing. So if x equals 0, we have y hat is equal to 51.6. What this means is that a car weighing 0 pounds gets 51.6 miles per gallon. Remember, x is the weight in hundreds of pounds. It weighs 100 pounds. So if a car weighs 0 pounds, it has a highway MPG of 51.6. Does this make sense? Hopefully you're like, yeah, no, because cars cannot weigh nothing. So this makes no sense. As we cannot have a 0 weight car, or cannot have a 0 pound car. But somehow give me an interpretation of what it means in the context of the situation for x to be 0. And sometimes x equaling 0 will make sense. Like if you had an equation about, I don't know, height after birth, x equals 0 could correspond to your height at birth, for example. So it's totally possible. It's just in many contexts, this might not make sense. Now imagine a regression line that relates average systolic blood pressure to age. And we know that the average blood pressure of somebody who is 20 years old is 120, while those who are 60 years old is 140. So given those 2 points, what is the slope of the regression line going to be? Well, recall that the formula for slope is y2 minus y1 over x2 minus x1. So we need to figure out what our points are. So x is age, y is average blood pressure. So age goes first in our ordered pairs. So our first one is 20, 120, and the second one is 60, 140. So y2 just refers to the second y, so we do 140 minus the first y, which is 120, over 60 minus 20. So the slope is 20 over 40, or m is equal to a half. And you can think about this as age increases by 1, the blood pressure increases by a half. You could also have phrased that as age increases by 2, blood pressure increases by 1. That's saying the exact same thing. Okay, part B says to find the regression line. What is the meaning of the slope and what is the meaning of the, if any, of the y-intercept? So far we have y hat is equal to 1/2 x plus b naught. So we need to use one of our ordered pairs to find b naught, and it does not matter which one you use. So I'm going to use 20, 120. If you use 60, 140, you're going to get the same value for b naught. That is a special property of lines. So input these points. 120 equals 1/2 times 20 plus beta naught. 120 equals 10 plus beta naught. Therefore, beta naught is 110. So our regression equation is 1/2 x plus 110. Okay, what is the meaning of the slope and what is the meaning of the, if any, of the y-intercept? So the slope we said is 1/2. We kind of already discussed this meaning. And it says as age goes up by 1 year, average systolic blood pressure goes up by a half. Now for the y-intercept, which is 110, this is the blood pressure of someone at age 0. So that might make sense, but babies are a bit special, and I don't know what their blood pressure usually is, so I'm going to say that this probably does not have meaning. But it's not as glaringly obvious as the previous example. So you could really argue that either way, but what I'm really checking is that you're telling me that you understand that this means the x is 0. That's all. And then finally, what is the estimated systolic blood pressure for people who are 70 years old? To figure this out, we just take our regression equation, we plug in 70. So remember, y hat was equal to 1/2 x plus 110. So y hat of 70 is a half x, half times 70, plus 110. So 1/2 times 70 plus 110. So half of 70 is 35. 35 plus 110 is 145. So on average, 70-year-olds have a systolic blood pressure of 145. Now, since we're talking about averages and not exact values, we would also like to know how much are our predictions that we get from this regression line, how much are they off by? And so that is something called a prediction error. So the prediction error is the difference between the observed value and the predicted value. The difference between the observed value and the predicted value. And remember that the observed value is the y, and the predicted value is the thing you get from y hat. So often, i.e., we say this is y minus y hat. Observed minus predicted. So observed minus predicted. Now the residual, this is a synonym for prediction error, and it's the word that's used actually more frequently. Synonym, synonym for prediction error. So residual is equal to y minus y hat. You actually can't abbreviate residual by R because R actually means something else in statistics. So just have to spell out residual, or you can write resid. So use the regression equation y hat is 577 minus 3x to compute the residuals for the following individuals. This is the equation relating age to maximum distance at which a road sign could be read from the previous lesson. So we have an 18-year-old, and the actual distance they can see is 510. So we know y is equal to 510. We need to find y hat. So y hat for an 18-year-old is going to be 577 minus 3 times 18, which is 523. So the residual is y minus y hat, or 510 minus 523, which is negative 13. So tell me, is this person below or above the average based on this residual? You can also get that from the numbers themselves. So he can see a sign at 510 feet. And average people, this person's age can see signs at 523. He is below average. So he, or she, I guess, is 13 feet Now for a 20-year-old, the actual distance they can see is 590 feet. Tells us that y is 590. And to find y hat, this time we input 20. So we have 577 minus 3 times 20, which is 60, and gives us 517. So here our residual is y minus y hat, or 590 minus 517, or 73. So this person is 73 feet above the average. Now, a reasonable question, now that we've seen these regression lines and worked with them and interpreted their slopes and their y-intercepts, is, well, how the heck, if you have that graph, that scatter plot of all these points, how the heck do you find the line that is the best fit? So you can kind of guesstimate and say, okay, well, I'm going to put a line through the most points possible that follows like the best trend possible. But that's a bit wishy-washy. I mean, what might appear the best to you might not appear the best to somebody else. So the technique used is called the least squares estimation criterion, and it depends on this residual stuff. So here is the long sort of form of what it says, then we'll talk about what it means. So the least squares estimation criterion says that the line for which the sum of the squared prediction errors and recall those are y minus y hats for the points in the data set is smaller than for any other possible line. Okay, so let's process this. So what you do is you consider all possible lines, and for all possible lines, you find the sum of squared prediction errors. That's called the SSE, and it's equal to a sum, there's that capital sigma again, of y sub I minus y sub I hat. And so remember that I means you take the first data point and you do the y corresponding to that data point minus the predicted y corresponding to that data point. And you add them all up. You do this for every possible line. And then you find the one that is the smallest. You want something called the minimum of this thing. So when your predicted errors is the smallest, that is the line squared. So when this sum of squared predicted errors is smallest, that is when you have found the line of quote-unquote best fit. And the reason that you square these things is because otherwise your over and underestimates would end up canceling each other out because you'd have some positives and some negatives. And I mean, this seems crazy. You're like, oh my gosh, I have to consider every single possible line. Well, it turns out you can use something called calculus to find the minimum of this, And you can figure out an equation that tells you what the line will be just based on the data you have. But the first thing I want to do is just work a little bit with this sum of squared errors thing and use it to decide which line is best given two lines. So the data for this exercise are given in the table on the right. So we are going to find the sum of squared errors for each of the following two lines. Line 1 is y hat equals 3 plus 3x, and line 2 is y hat equals 1 plus 4x. So the question is which line is a better fit according to that least squares estimation criterion. So we need to find the sum of squared errors for each line. And remember that SSE is the sum of the y's minus the y hats squared. So first we need to find all these residuals for both lines. So first let's look at line number 1. So line number 1 is y hat equals 3 plus 3x. So first we're going to need all the predicted values. So y hat of 1, and I'm choosing to plug in the points that were given for x in my table. So plugging in 1, we have 3 plus 3 times 1, which is 6. Y hat of 2 is 3 plus 3 times 2, which is 9. Y hat of 3 is 3 plus 3 times 3. So 3 times 3 is 9, plus 3 is 12. And then y hat of 4 is 3 plus 3 times 4, so that's 12, 13, 14, 15. Okay, so those are all the predictions. Now let's find the residuals. Remember, that's y minus y hat. So first we have y sub 1 minus y sub 1 hat. So first y minus first predicted y. So that's 4 minus 6, or negative 2. Second y minus second predicted y. That will be 10 minus 9, which is 1. Third y minus third predicted y is 14 minus 12, which is 2. And then fourth y minus fourth predicted y is 16 minus 15, which is 1. And the sum of squared errors for line 1, you take these things and square them. So negative 2 squared plus 1 squared plus 2 squared plus 1 squared. And this should be, so we have 4 plus 1 plus 4 plus 1 for this first line. Our sum of squared errors is 10. And we're going to repeat that process for line 2. So line number 2, which is y hat equals 1 plus 4x. So y hat of 1 in this case will be 1 plus 4 times 1, which is 5. Y hat of 2, 1 plus 4 times 2, which is 9. Y hat of 3, which is 1 plus 12, so 13. And y hat of 4, which is 17. Look pretty close. Then we'll find the residuals. So first we will do four minus 5, which is negative 1. That's for the first y and first y hat. Then 10 minus 9, which is 1. Then 14 minus 13, which is also 1. And 16 minus 17, which is negative 1. And in this case, the sum of squared errors, so take these all and square them, because first you underestimate, then you overestimate, overestimate, underestimate. So negative 1 squared is 1, 1 squared is 1, 1 squared is 1, and 1 squared is 1. So in this case, the sum of squared errors is 4. And you want the line for which that is the lowest. So by this criteria, who's better? Is the first line better or the second line better? It should be pretty obvious that the second line is better. So by the least squares estimation criterion, which of the lines in part A was better? And the answer is that line 2 is better. And the reason is because it has a smaller sum of squared errors. Now, on the previous example, we decided what line was better, but I gave you 2 lines to choose from, and we just looked at which one had the smaller SSE. So the question is if you just have sample data, where does that regression line come from? And here it is. It's kind of a long, nasty sum formula, so we're going to make you do it just once as an example in class, maybe on a homework assignment, maybe a test, but you'll get to use notes. All right, so here is what y hat is. Y hat is b1x plus beta naught, where beta 1 is found by doing xi minus x bar times yi minus y bar over xi minus x bar squared. And this is for all the things in your data set. So remember that the x sub I, these are the x values for your data. Y sub I are the y values, both from the data. X bar is the average of the x values. Y bar is the average of the y values. So what you do is you take every x value minus the average times the y value minus the average. So that'd be x1 minus x bar, y1 minus y bar. So first x minus the average x times first y minus average y plus second x minus average x plus times second y minus average y. All that added together divided by the sum of the xi, so the x values minus the mean of the x's squared. And that tells you beta 1. This one is nastier, but you have to find it first. Once you've found that, finding beta naught is super easy. So from that, beta naught is y bar minus the beta 1 you just got times x bar. So this is really sort of hard to explain without doing an example with numbers. Let's do one with numbers. So for the following data set, we're going to find the equation of the regression line by hand, and then we're going to sketch the data set and overlay the regression line on the plot. So first thing you should do is find x bar and y bar. So the average of the x's will be 4 plus 1 plus 3 plus 2 divided by 4, which works out to be 2.5. And y bar is 5 plus 0 plus 4 plus negative 1 over 4, which works out to be 2. Then the next thing you do is you find beta 1, and recall that's equal to the sum of xi minus x bar, yi minus y bar, all over another sum of xi minus x bar squared. Now, because you have 4 points, this I is going to go from I equals 0, 1 to 4. And what that's telling you to do is first you plug in 1, then you plug in 2. then you plug in 3, then you plug in 4. So let's do that. So beta 1 equals, so first we input 1. That's going to be x1 minus x bar times y1 minus y bar plus x2 minus x bar, y2 minus y bar plus x3 minus x bar, y3 minus y bar, and then plus x4 minus x bar, y4 minus y bar. We'll put in specific numbers in just a sec. All over, same thing. x1 minus x bar squared, x2 minus x bar squared, x3 minus x bar squared, and x4 minus x bar squared. And just the fact that there's like a whole ton of numbers here can suggest to you that probably this is a good thing to do with technology most of the time. So most times software calculates this and you don't do this by hand. But just this once, let's fill in numbers. So x1 is the value of our first x, which is 4. X bar is 2.5. So 4 minus 2.5 times the y1 is 5. Y bar is 2. Okay, x2 is 1 minus 2.5, 0 minus 2. The third x is 3. The third y is 4. And the fourth x is 2. And the fourth y is negative 1. So there's all the stuff in your numerator. All of that is over, well, first x, 4 minus 2.5 squared, 1 minus 2.5 squared, 3 minus 2.5 squared, and 2 minus 2.5 squared. So working chunk by chunk, first we have negative 4.5 plus 3 plus 1 plus 1.5 in our numerator, all over 2.25 plus 2.25 plus 0.25 plus 0.25. And adding all this up, we see that we end up with 1 over 5. So the slope is 1/5. And that is the hard part. Once you've got that, the rest of it isn't so bad. Remember that beta naught is equal to y bar minus beta 1 x bar. And from the beginning, our y bar was 2. Beta 1 is 1/5. X bar was 2.5 or 5 halves. So this is the same thing as 2 minus a half. Which is 1.5 or 3 halves. So that tells us that our regression line, y hat, is 1/5 x plus 1.5. Now we're also asked to sketch the data set and overlay the regression line on the plot, so let's do that. So sketching our data set, we first need a grid, and our x's range from 1 to 4. So 1, 2, 3, 4. And the y's range from -1 to 5. 1, 2, 3, 4, 5. All right, so we have the point 4, 5. Roughly speaking up there. 1, 0, right there. 3, 4. and 2, -1. Okay, so the regression line, remember that we had y hat was 1/5 x plus 1.5, so it started out at 1.5, and it would rise 1 and run 5. So it ends up looking something like this, which I guess at first glance doesn't look super, super great, but it has to balance out all these points. And really this point right there kind of like pulls it down a bit because that point is lower than the point to the left of it. So that's how you find a regression line. And mostly it's just going to be done with software because it is really, 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 really tedious, as you just saw. Now, once you have a regression line, a good question is, how good is my regression line? How strong is this relationship? And the thing that you use to measure that strength is something called correlation. So correlation, this is the number that indicates the strength and direction of a straight line relationship. And direction means, is this a positive association? In that case, you have a positive correlation. Is it a negative association? In which case you have a negative correlation. Now, some things about correlation coefficients. They're always between -1 and 1. And they're kind of like percents, really. You either have a 100% perfect relationship in the positive direction, negative 100% meaning in the negative direction. Now, the magnitude of the correlation indicates the strength. And the strength is the closeness of points to a straight line. So points that fall really, really, really close to a straight line are going to be more strongly correlated than ones that have more wiggle. And a correlation of 1 or -1 means that there is a perfect linear relationship, and all data points fall on the same straight line, like this, or like this. And then the sign of the correlation indicates the direction of the relationship. A positive correlation means that the two variables tend to increase together. And a negative correlation indicates that when one variable increases, the other is likely to decrease. Like performance on a sobriety test and alcohol consumption. A correlation of 0 indicates that the best straight line through the data is horizontal. So something like this, and no information is gained. As x increases, you don't know what happens to y. Nothing might happen to y. All right, first, which of these numbers could not be values of a correlation coefficient? Why or why not? So there are two of them, -1.7 and 2.5. And the reason is that correlation coefficients are between -1 and 1. These numbers are not. So it's totally not possible to have correlation coefficients outside of that. Think about them kind of as being percents. Now for each pair of variables, identify whether the pair is likely to have a positive correlation, negative correlation, or no correlation. So hours of television watched and GPA. Would you expect that as hours of television watched goes up, GPA goes up or down? I'd say probably down. So this is probably going to be a negative association. And we'll say that as hours of TV watched increases, GPA is likely to decrease. No, we can't say that watching TV causes your GPA to go down, just that as hours of watching TV goes up, it's associated with a decrease in GPA. And the whole fact that there doesn't be a causal relationship between things just has weird stuff like this happening. Number of liquor stores and number of ministers. Okay, I don't really think it's that the ministers are trying to save the drinkers or vice versa. It's just that you would expect that if you're in a little small town, so we'll say we put number liquor stores, number ministers. Well, small towns are going to have low numbers of liquor stores and low numbers of ministers. Big towns will have lots of liquor stores and lots of ministers. So, and there'll be some variability, but probably as number of liquor stores goes up, so does the number of ministers. This is probably going to be a positive correlation. No, nothing says there's any cause. Liquor stores aren't causing ministers, ministers aren't causing liquor stores. So as the number of liquor stores goes up, so does the number of ministers. And the variable kind of lurking there in the background, some books actually call them lurking variables. Actually, they're kind of like hiding back there and messing with stuff. The lurking variable is population. It's the size of the city causing these things to go up. As the size of the city increases, so do the liquor stores and the ministers. It makes it seem as if there's a relationship when there's not. Okay, performance on a strength test and age for people between 40 and 80. So as age increases, what do we think is going to happen to performance? I'd suspect that your strength goes down. So performance will likely decrease. It isn't all fatalistic. It doesn't mean you can't sort of like delay the onset of that loss of strength, but on average, your strength will go down. So this is likely to be a negative association. Now, R is the number that is used for the correlation coefficient. And remember that R is in between 1 and -1. And there is a really useful interpretation of R squared. So first of all, if R is between -1 and 1, what happens when you square all those numbers? So first of all, if you square 1, you're never going to get anything bigger than 1. But things like -1, that squares to 1. -0.5 squares to +0.25. So you take and you square all the possible r's. The smallest value that r squared can be is 0. Now, here is where this r squared number comes from. And we'll explain what those things mean. So first of all, SSTO, as your book defines it, is the sum of squares total. Now what this is the sum y sub I minus y bar squared. This is often called the total variation in y. It's looking at how much does y vary from its mean. And the reason for squaring there is because otherwise you'd have variations above and below the mean canceling out. So you square to accommodate for that. And recall that SSE, that was the sum of squared errors. So that's the sum of y sub I minus y sub I hat squared. This is the sum of square errors. And what this tells us then, r squared is the proportion of variability of y explained by knowing x. So how much information does knowing x give you? And so the x is kind of like built into this thing because it's used in finding those estimations. So SSTO minus SSE, that gives you the difference between the total variability and then how much error you have divided by the total, and that's what gives you the proportion. Another thing to also observe is that if SSE is about equal to 0, meaning you have very, very, very little error, then r squared is going to be really close to SSTO minus 0 over SSTO, which is 1, meaning that you have pretty close to a perfect relationship. Perfect relationship meaning very little errors. So basically, if this error is higher, that's going to decrease the r squared. If the error is lower, that's going to increase the r squared. And that tells you how much you know about y given that x variable. You don't have to explain this whole thing, you just have to use it to answer some questions. So the correlation between height and stretched right handspan is r equals 0.74. So squaring that, we find that r squared is 0.55. And this tells us that 55% of the variation among observed right handspan is explained by height. So height explains 55% of that variation among the observed right handspans. Compare that to the television hours watched and age. So this has a much smaller correlation coefficient of 0.136, which when you square it gets even smaller, and it's 0.0185. And that means that age explains only 1.85% of the variation among observed amounts of television watching. So that's quite low. And then lastly, suppose you know that the regression line is y hat equals 10 minus 3x, and the value for r squared is 90%. What is the correlation between the two variables? In other words, what is r? Well, you know r squared is 90%, or r squared equals 0.9. So therefore, r is either positive or negative the root of 0.9. So r is about equal to positive or negative 0.949. And the question is, which one? Is it the positive correlation or the negative correlation? And to figure out which one, you need to look at the regression line. Notice that the slope is -3, which means we have a negative association. And if we have a negative association, r must be negative. Thus, our r is about equal to -0.949.